forward here and continue from where we left off. So let me get the program set up. Good. Right. Okay, so let's all assume, hopefully we are in all the right class today. This is ECNG 2011, right? So if you're not supposed to be here and in the other class, well then you could relax a little bit. Okay, all right, so where we ended last time, we've done a couple of topics so far. We have, in the course of everything last week and up to this point, we've done a review of sampling on how it's done, a little review of some of the properties of the Laplace transform via its some of the things that we use, like the final value theorem and the initial value theorem. We've looked a little bit at block diagrams and block diagram simplification and some of the manipulations that are required to work to simplify diagrams that are presented to you. And then after that, we looked at how to draw the Bode or Bode magnitude and phase plots, how to take the transfer function and break it down. And in the course of that, we went through the lectures on the behavior of things, the poles and zeros and so on. There's another part that we'll come to a little bit later on. This was just this straight line answer for this particular part of the question here. A fairly straightforward one. There'll be more complicated ones that we still have to look at and that you will attempt as we go forward. Right. This was just some discussions on it, how you combine, because some people were asking how to combine the various the various asymptotic plots into the overall master plot here. Right, and then last time we met, which was Friday morning, we spent some time talking about the Fourier series and the Fourier transform, and going from one to the other, where the Fourier series started and how we went from the series to the transform, and then using some of the properties of the transform, and we spoke about all of that as well. So today now we're shifting, and I'm just following the context, the sequence of topics as it appears in this particular past paper that we're looking at, not necessarily how it was done. Okay, this actually would have been the last set of topics that would have been done in the course, and it deals with discrete time systems and this business called the Z transform. And here you have now, remember from question 1, that the course deals with two sets of things. We deal with continuous time signals, and we also deal, and the nomenclature for it is something like this. We also deal with discrete time signals. The continuous time signals are the ones that exist for all time. All right, and of course, in our case, if you remember, in practical engineering terms, there are certain signals, although they can exist for all time, they start only when we basically initialize them, and we call those causal. All right, typically starting at t equal to 0. So we pick a start line for it. Discrete time systems, some of them are causal, some of them are not. And just a quick review on that, remember you can have things like stored data, like the data on a file, or the videos that are recorded from the lectures that we're doing now. You can jump into the middle of the lecture and continue from that point. So from the point of view of a user like yourself, that the recording is not a causal recording. It doesn't start when you start to look at it. It just so happens you are observing it at some point in time, but it was going on even before you started, right? So discrete time systems and signals have that property, that because you can jump into it at any point in time, that you could really it is not, it doesn't, it was going on even before you looked at it. So it doesn't, many of them may or may not be causal. All right. So let's start the review before we get to these things. So the, what do you call it? The continuous time transfer function we've seen already would have been a function of S. So the equivalent transfer function for this would have been something that you met before. Most likely would have looked something like this: S squared plus 2S plus 4 over S cubed plus 3S squared minus S minus 3, right? The continuous time equivalent, UIVALENT, right? Right? Would have looked at it. Now, these are, I'm not saying anything about these being equal. I'm just showing that what we have been looking for, or what I've been looking at generally up to this point, would have been something looking like this. Once you start to go from continuous time to discrete time, the systems that handle these kind of inputs would have transfer functions now that are a function of another variable. Instead of S, it's a function of a variable Z. And we'll get to it, why we use that. Once you have that now, all of the operations that you're accustomed doing with continuous time transfer functions, like partial fractions, for instance, are also applicable with this other variable as well. Okay? And then having gone to whatever this other variable is, you have to be able to go back and forward from those two domains. So exactly like we would have done with the Fourier, with the Laplace transform, exactly like we would have done with the Fourier transform, this other domain also has the ability to go into it and to come back home. Okay, so let's go briefly now and review what that particular domain looks like and how we ended up getting here, why we need to get there in the first place, right? What it is about. Just now, where am I? Let me just try to get this. Just keep here. So go here. This one. There we go. I am sharing. No. Oh, there we go. This one. This is the one that we want to share. Good. Right. So we'll just go. When we had done this particular review, we had done a little type of example where we were developing a type of equation. It just so happened that this equation was something to do with repaying a loan. But in doing that, we landed up with something called a difference equation. All right. And what we said is that in contrast, when we're dealing with a continuous type domain, we have been using something called differential equations. But in a discrete time, instead of the differential equation, what you have is that the systems are described by something called a difference equation. And the difference equation, of course, instead of having a dx dt in them, will typically have an x minus, sorry, like a k minus 1 or x k minus n type of descriptor in it. In our case, dx dt in the continuous time domain led us to something called our first order differential equation. And then, of course, if we had d2x dt squared, you had a second order, etc. In this case, if you have a k minus 1 in the difference equation, that's a first order. And then if you have a k minus n in it, that's an nth order. Right? So k minus 2 would have been second order, k minus 3 third order, and so on. Right? And then what we did is that we showed a little bit about how, first off, they sort of, what shall I say, where you can get a difference equation from a differential equation. And we saw that from your add maths. When you were learning how to find derivatives, what you did was to take, if you want to find the derivative of this curve, the black line here, what you did was to take 2 points on the line, on the curve, sorry, you join them by a line, and then you found the slope of the line this way. And then what we did is to make these points move closer and closer together. So eventually what would happen is that the line would move closer and closer together. And eventually, when these 2 points coincided, what you had was a line, you had created a line that was at the tangent of the curve. And at that point in time, the slope of that tangent was the slope of the curve at that point. And this is where we got our dy dt or dx dt or dy dx behavior from. But as we can see, there's a relationship between this and finding the difference between two consecutive points on the same curve. And that is the relationship between the difference equation and the differential equation. So in other words, if you took the curve and you sampled it, then as far as this is all you are aware of, once you sample it, all you are aware of is these 2 points here. You have no idea what is happening in between here at all. Your world, the sampled world only exists around these 2 points right here. So if you want to find out what is the slope or the gradient between those 2 points, then you work it out from first principles here. And you get the equivalent here, which is the difference equation that is giving you an approximation of your dy dt and so on. All right. So that was the one thing. And then in terms of the system behavior, discrete time systems are modeled using these difference equations, therefore. So inside of here, all of these equations that just deal with a set of numbers and delayed versions of the numbers, and you get numbers going in, numbers going out. All right. And how you solved it was that if you were given, go back to what you had done before. If you given this in calculus, you know that to solve it, what you have to do, because what you're trying to do is to get yt, this solution here. To solve this, you have to integrate this whole thing. So you have dy dt equal to something. So you could take the ay here and you put it across here, ayt. And then if you integrate this now, and you integrate this, then substitute whatever you have back inside of there, you can get an expression for yt in terms of everything else, right? That's how you solve a differential equation. And you learned all sorts of tools to do that, integrating factors and so on, if it was simple enough. Once it was more complicated, we decided to use, and we discovered another tool where the differential equation, when you use that tool, you went from this domain here into another domain where the dy dt's were converted into products. So you got this s, y, s, and so on, right? And we call this, of course, the S domain, and we use to go from one to the other, we use this thing called the Laplace transform, right? Unfortunately, difference equations now, the way to solve the difference equation is to use something called recursion. And I believe in one of your math courses in ECNG2013, I believe when you do some discrete mathematics, you do a little bit of solving equations by recursion. It isn't an easy thing to do, because what you have to do is to solve and then look for patterns. And I'm sure you would have done that in your CAPE math and CSEC math and so on as well. But solving it by recursion, again, is kind of like solving a differential equation by hand. It is a little bit tedious, and it takes time. And if you make a mistake, then you end up going along the wrong road, and you end up not getting the answer. So what we said is that this is all well and good, and if you use recursion, you could get a solution to it, a general solution, of course, meaning that you're getting y, k, and you understand, of course, whenever you see k, that it really means kt, because this was y of t sampled at intervals of t seconds, microseconds, t units, and t units of time, whatever those units are, right? And of course, the more correct thing I've been saying is to use square brackets, right, to indicate that there's a set of numbers rather than continuous time, right? So you remember those sort of things. But and of course, like the continuous time domain, if this is it, you have an input, which is x, you have an output, which is y. Anything with a y0 in it is what we call the initial condition, and so on, which is just like our difference equation and our systems from what we have done, what we did early on in continuous time, right? So, and this here just summarizes a little bit about what we were saying, is that the system, discrete time system, responds to numbers. The input is a series of numbers, the output is a sequence of numbers, okay? Right, so after we did all of this thing, we said, okay, there has to be a better way to look at it. There must be a better way to solve it, and in as much as we have the Laplace transform working for the continuous time domain, there must be some kind of equivalent in the discrete time domain for us to use. And this is where now we said, okay, that let's look at another tool that exists, right? So let me go back here. I'll stop sharing this. Share this one now, this. Okay. Right, so these are lectures. These would have been the last set of lectures that were done, lectures 25 to 28, the last set of lectures that we did in class. Right, so you have all of that. Right, one of the things that, so what we said, okay, well, we have the Laplace transform already. Isn't there some way we could use a Laplace transform with the discrete time signals? Unfortunately, it doesn't work well. And what it tends to do, because of the sampling process, that the Laplace transform, when you take a system, if you take the discrete time and you try to apply the Laplace transform for it, remember sampling, you get sampling by multiplying a continuous time signal by a sampling train, which is a series of impulses. These impulses here. Right, so this is how you get the sample signal. Right, and then this gives you your y and t. Unfortunately, if you apply the Laplace transform to this, this infinite sampling sequence here creates a series of infinite poles. So that what happens is that instead of getting a nice clean transform, what you get is that, for instance, instead of, let's say you were expecting something like 1 over s plus 1, right? Because of the sampling process, what you end up getting is something like 1 over s plus 1 to the power n. So all of these, so this is not going to help us. In other words, it's going to take what should have been a simple situation and instead give you something like this, which is not going to help us. You're trying to solve an equation, not create an infinite set of problems for yourself. So a different transform is required. And this is where this particular one came in. And we said that this had to do with complex analysis. We didn't go into the derivation of this. Neither did we go into the derivation of the Laplace transform because of how they are, the mathematics involved. We were using the result. But this particular transform now was a function. We're dealing with a complex variable z. Just like the Laplace transform, S is complex. S is a complex number and it has a real and an imaginary part. Z is also complex. So if we take the discrete time signal and we apply the Z transform, this transform to it now, we create a function that is now in a different domain. So you're going from the discrete time domain into this Z domain. And notice, because you're dealing with a series of numbers, remember these numbers will be 1, 7, 5, 4.3 minus 2, that kind of thing, right? X, K, T, oops. Could be something looking like this, right? So it has a value at t equal to, let's say t equal to 0. It has a value at t equal to 1 or t equal to 2. There's no value in between here. So there's no value at t equal 1.1 for argument's sake. So you only have a set of values inside of here. So therefore, the transform cannot have an integral. An integral is a continuous time behavior. So instead, it turns out that we have a summation. So you're just simply summing some values, and you have this power series in some variable called z. Right? Later on, I said that if you do discrete signal processing, if any of you all take this ECNG2011, you will actually see how it is really related to the Fourier transform. That's how the Z transform kind of comes about, right? So in the world of transforms, if you like, it's not really part of this course. You have the Laplace domain, you have the Fourier domain, and then you have the Z domain, and they're all related. So basically what you do is that you could get from S, from the S domain to the frequency domain, and then if you sample in the frequency domain, you can get to the Z transform itself, okay? Okay, so just excuse me a second, please. Right. I happen to be acting head of department now for the next 3 weeks. So I'll be getting some calls in between. Sorry about that. Yeah. So there's a little relationship here, and actually there's a relationship going back this way as well too. Not part of here, but just to let you know, this is why I keep telling you that when you do the course, all you really have to know is one of the transforms very good. Usually the Laplace transform, and if you know that, you could kind of figure your way around the Fourier and to some extent the Z transform as well. All right? So using that now, we were able to derive some transforms like we normally do. And remember, it's a power series. Okay, it's a power series in negative powers of Z. Okay, so like for instance, if you were to expand the what do you call it? This, if you were to expand the one-sided version, just for argument's sake, it would be x0, z0, xt, z minus 1, x2t, z minus 2. So for instance, if x kt was equal to 5, 7, and 4, right? This is x naught, this is x t or 1, x1, x2t or x2. The z transform of this would have been 5z to the power naught plus 7z minus 1 plus 4z minus 2. And of course, z to the naught is 1. So the answer for this would have been 5 plus 7z minus 1 plus 4z minus 2. As easy as that. Right? As easy as that. A direct read. So if you have a sort of finite set of values for KT, you can just simply read out the Z transform directly from those values. All right? So you don't have to go to tables and so on. Feel free to interrupt if there's anything that you remembered or you forgot from the last time that you want clarified. Huh? Right? So again, we made a little point here that like the Fourier transform, like the Laplace transform, there are some conditions where the transform may not exist. What that has to do, remember, this is a power series. So for xz to have an answer, the series has to converge. In other words, the series has to end at some point. The limit of this summation, right, has to come down to some finite number when n approaches infinity. If not, then you have a transform that doesn't end, which is not going to help you at all. Right? There are some things like that where the transform will not end, and in that case, that set of values cannot have a Z transform. Just like certain things cannot have a Laplace transform, or certain things cannot have a Fourier transform. Remember last week we spoke about signals looking like the chirp signals, where the frequency could start very high and it goes to low, and then there's a discontinuity here, and it starts back very high and it goes low. We said that something like this cannot have a Fourier transform. Same way, certain types of signals cannot have a Z transform, and so on. All right? Just to be aware of that. And then, like we do with all our transforms, we find the transforms of some typical signals. The unit pulse, which is the discrete time equivalent of the unit impulse. In other words, there's a value at t equal to naught and nothing else, and the value is 1. And like the continuous time unit impulse, remember the unit impulse in continuous time is really a definition that the integral of delta t is equal to 1. In other words, the area of the impulse is 1. And in reality, the continuous time impulse is supposed to be 0 with an infinite height, which doesn't exist. The discrete time version is simply a value of 1, right? So no areas or anything involved, it's just a value of 1 at t equal to 0. And the Z transform of that is 1, right? And the unit step, the discrete time unit step, again, is a series of values 0, 0, 0, 0, 1, 1, 1, 1, 1. And the Z transform of that, if you go directly, it's going to be 1 plus Z minus 1 plus Z minus 2 plus Z minus 3, etc. And you work it out like that. Remember, if you expanded, this would have been 1 by Z to the naught plus 1 by Z minus 1, oops, plus 1 by Z minus 2, etc., etc. So it's 1 plus Z minus 1 plus Z minus 2. And we said that if you remember now, this is a type of thing called a geometrical or geometric progression from your mathematics. And there is a way this can sum to infinity. And if you could sum it to infinity, then the sum to infinity is a over 1 minus r, where r is the common ratio, right? The common ratio for here is Z minus 1. The first term, a is 1. So that if you sum to infinity, the sum of that 1 plus Z minus 1 plus Z minus 2 plus Z minus 3, the sum to infinity of that is 1 over 1 minus Z to the minus 1. Remember, again, from your add maths or wherever, the sum to infinity only converges if the common ratio is less than 1. Right? You're trying to remember that. If you remember that going back a few years, if the common ratio is less than 1, then that is the only time a GP will converge. So in this case, the common ratio is Z minus 1. So the only way this thing could converge is if mod Z minus 1 is less than 1. Remember, Z is a complex number, so you have to talk about the modulus of it. So this could only occur if mod Z is less than 1. And we change that around a little bit. If I tell you that mod Z minus 1 is less than 1, remember, as we said, Z minus 1 is equal to 1 over Z, right? So if mod 1 over Z is less than 1, then if I flip this around, I'm saying that Z has to be greater than 1. All right, if I take the inversion, the sign inverts, and what is mod Z greater than 1? What does that look like? Mod Z equal to 1, if you remember, your complex numbers. So if Z is equal to some A plus J, B, and I'm telling you that mod Z, for instance, let's say is equal to 1, right? Forget the greater than for this time. If that is equal to 1, it means that A squared plus B squared is equal to 1, right? And what is A squared plus B squared equal to 1? If you remember, A squared plus B squared equal to 1. If this is A and this is B, A squared plus B squared equal to 1 is a circle of radius 1, right? So if I'm saying that mod Z has to be greater than 1, A mod Z equal to 1 is a circle. So if mod Z has to be greater than 1, it means that anywhere outside of that circle is where this particular expression will converge. In other words, where it will have to have an answer. Everybody following that? Yeah? Remember that?
Yes, sir, I understand.
Right? And because it was a radius of 1, we call this particular thing the unit circle. And the radius of conversion is everywhere in the blue zone outside of the unit circle. And just remember this, the z-plane uses polar coordinates instead of Cartesian. All right, typical complex number business when you're dealing with a magnitude and a magnitude and an argument for it, right?
Excuse me.
Yeah.
So like a question to come out exam paper, like to draw what you're gonna represent. So you have to like draw the circle with the radius 1 and then state like outside of the circle is where it will intersect.
Yeah, I could ask you that. For instance, I think later on in these slides as well too, there are certain things like let me just show you. I'll go past here. Right. So for instance, a transfer function looking like this, where xz is 1 minus az minus 1. If I were to ask you, for instance, what is the region of convergence of this? Again, this will only converge if this is the common ratio here is less than 1. Okay, here we go again. Half a second. Right. Okay, so right, so the common ratio here now is this will only converge if az minus 1 is less than 1. And that is, to answer your question, the unit circle is red, but mod z equal to a is a circle of radius a on the inside here, right? So therefore, the radius of conversion of this particular one will lie anywhere outside of that, right? So I can ask you to draw something simple like that. I wouldn't, no, should put the hours in X-ray. Right? Yeah, I wouldn't normally ask you to like a big complicated transform to tell me where the region of convergence, but something like this, you should be able to know it as well. Yeah.
Okay, thanks.
All right. And then what we did so we were here, right? And then we compared it with the S-plane. And while I have it, while we have it here, notice that here I have positive indices of Z. The transform is defined for our purposes in terms of negative indices. Let me go back to where the transform is yeah, right? Now, this, I also mentioned this, that in some books, you also see it in this form. So you have the summation, you have x, k, t, and you have it, what do you call it? By 1 over z, right, to the power k. So that is another version of it that exists, because z, z to the power minus k is equal to 1 over z to the power k. All right, so these kind of transforms here, like this here, some math books will have it like 1 plus 1 over z plus 1 over z squared, etc. In engineering work and for our work, and especially discrete time controls and signal processing and the like, we prefer it in this form because it relates exactly to what the signal is doing. For instance, we know that if I have, let's say 1, 2, 3, this is my x, k, t here, right? This is x naught. Yeah, give me a second again. Right. So X, right. So that one is X1. This is X minus T, and this is X minus 2T. Right? Remember when we were manipulating signals, that we said that if I moved in this way, this was a delay, and moving in this direction was an advance. The delays give me, if I delay by 1, which is the next sample here, this gives me the Z minus 1. Delay by 2, I get Z minus 2. So for our purposes in engineering, every time you see, if you leave it in this particular form, we already know that the minus 2 is equivalent to minus 2T, which means this was a signal that happened at T equal to 2. In other words, after we started at T equal to 0, and 2 sample times down the road, this particular sample was extracted. Right? In other words, there was a delay, if you like, of 2 sample periods before this particular sample was extracted. So this tells us exactly, it describes that behavior exactly for us. Whereas when you leave it in this form, which the mathematicians like because it's easier to work with positive indices and negative indices, it doesn't tell you the truth. It's nice for mathematics, and it's nice because you're dealing with a transform because you like the calculus and the math. You're not dealing with a transform because you're trying to find a practical application or try to analyze something that is actually happening, right? And that's the difference between applied science and pure science. The pure science is this here, right? The pure science is looking at this transform in this way. The applied science is what we want and looks at it in this particular form, which, as I say, relates directly to when the particular samples were happened, were taken, sorry, yeah? All right, so that's just to clarify that little point there. Right, as we had it here. Right, so you're comparing the discrete time unit step with the continuous time. All right, and we saw that in the case of the continuous time unit step, that the answer converged everywhere on the right-hand side of the S-plane. Right, this only converged on the right-hand side of the S-plane. The discrete time version converged outside of the unit circle. So in other words, if you want to map one plane to the other, right, the right-hand side of the, well, let me go back here before I get to this one. The right-hand side of the S-plane maps to the outside of the unit circle. And we already said in some of our continuous time discussions that for stable systems, for stable continuous time systems, we want poles to be on the left-hand side of the S-plane. So a stable system in continuous time domain, in the continuous time domain, has the poles located on the left-hand side of the S-plane, which maps directly to inside of the unit circle. Okay, so that was the sort of comparison here. So if you have a stable system, right, once you do the, you have a stable system in the S-plane or the continuous time domain. If you sample that system, for it to be stable, the poles that you create have to land up inside of the unit circle. Okay, this is something you're going to meet quite a bit if you're doing controls with Dr. Ramlal. Okay, and he's going to pull back some things here on the discrete time controls. He's going to pull back a lot of things from this for you as well. Okay, because they use Z transforms exclusively for that. Right, based on power, we did this. Right. So that was the introduction part of the Z transform. And then the other bit we had to do here was share number, slide, where are we? Slide number 27. There's a, right, there we go. All right, and then we started to compare, because as I keep saying, if you know one transform very good, and the one that you happen to do the most work with is a Laplace transform. So if you know the behavior of that, then the properties here are and there's a term to use here, broadly similar. Okay, there are differences, but if you know what is similar, then it's easy to figure out what is not. Right? So the Z transform, there was a table of transforms and so on here, right? Which you given. This one, when you shift in time, this is what we were just talking about. So if you shift in time, then whatever was the original Z transform, you multiply it by Z to the minus whatever the shift was. You remember in the Laplace transform, if you had dy dt, that gave you a y s, sorry, an s, sorry, yt gave you a ys, dy dt gave you an sys, d2y dt squared gave you an s squared ys, plus some things. We will plus there were some additional things that come in here. We'll get in a while. The Z transform gives you a similar sort of thing. So xn, right, a signal xn will give you a Z transform xz, xn minus 1 or minus t will give me z minus 1 xz, right? You take xn and you delay xn by 2. You get z minus 2xz, right? So the same sort of thing. Of course, the signs here are a little bit different, okay? But if you remember this, you could kind of rationalize all this. And plus, there are some extra bits that come in here as well, like the Laplace transform, right? The initial conditions, you remember those? So the y minus t, y minus 2t, same thing with here, all right? So these properties are here, and this one, of course, that we know all the way through, that convolution in time is a product of the transforms in the transform space. And in fact, this discrete time convolution is how we learned to do continuous time convolution. And we'll do that review in a second. Okay, the office again. Yes. Right, so yes, we are done that, and we're going to spend some time talking about this continuous time convolution, just to make sure you have your handle on that. Okay, we did this, we just spoke about that, and the explanation of the properties here, how to prove the property. Right, I don't think you could look at this. This was fairly easy. Anybody didn't understand? If you remember when we did the properties of the Z transform, when we discussed proving the properties, anybody had an issue with that? Right. It's fairly straightforward, but if you need to, let me know. Right, delayed summation. This is all the proof of the properties here. This is okay. Right. And then we got to the stage now where we looked at how to apply the Z transform now to a difference equation, which is what we're trying to solve in the first place. So if you apply the Z transform, you could look at the difference equation straight off. So for instance, this now will give me a Y Z, right? This will give me an A naught into Z minus 1 Y Z plus Y minus T, right? And here you would have B naught into Z minus 1 X Z plus X minus T, and here plus B1 X Z. Okay, remember the little difference here in that the Z transform adds the initial condition here. The Laplace transform subtracts it. So the equivalent Laplace transform would have been something like S, sorry, back here, would have been S Y S minus, right, Y naught. Yeah, remember that? So there's a difference. You have to remember here that is the Z transform adds the initial condition, and the proof is the previous couple of slides in this lecture, whereas the Laplace transform subtracts it. Right. So once you apply that, you could get the move from the difference equation to this, which is the Z transform and the transfer functions, and we have the same sort of responses that we were dealing with. Okay, the initial condition response, the input response, and the output response. Right? So we go back to the where we are at. So in terms of discussing the where's the class? Where is the we were talking about? Yeah, I can't find the paper. Ah, there we go. Trying to find back my the class that we were supposed to be discussing. Which paper we are discussing? The 2006 paper. Right, there we go. There we go. There we go. There we go. Right. Right. So let's get this here and share the stuff. Choose off. What is this? Nice. Right. So you get to the, just to sort of summarize what we've done so far, you apply all of that, and when you simplify, you get something looking like this. And now to express this in partial fractions, we look at on Wednesday morning. Remember, the same rules apply for this for partial fractions now, in that you have to factorize this. If I give you something to factorize, then first off, if you have a Z to the minus 3, you know that you're going to have 3 factors here. Z minus 1 plus or minus A, Z minus 1 plus or minus B, and Z minus 1 plus or minus C. All right? Usually, if I give you something like this and no other information, it means one of these factors, A, B, or C, is either plus or minus 1, 2, at most 3, right? So you try 1, for instance. So you let Z minus 1 equal to plus 1 and see if, and use a remainder theorem to see if that is a factor, and then the rest will will work out. What I told you all too is that some people may not like to work in negative indices and prefer to work in positive indices. What I suggested is that in that case, until you got accustomed to it, let z minus 1 be equal to something like a. Don't use s, don't use x, y, z, or anything like that. Pick some other number some other letter in the alphabet and plug it in. So this will be a squared plus 2a plus 4, right, over a cubed plus 3a squared minus a minus 3. And then you could work out your fractions and then substitute. If you're asking to do it in partial fractions, don't do this one, which is a multiplied by z cubed over z cubed. In other words, don't rationalize this into positive indices. You're going to get a different answer, and I'll talk to you and tell you why that happens. All right? So what you will do is that if you're not comfortable working with negative indices, take z minus 1 and substitute a positive letter for it, except x, y, z, or s. Don't use those. And then solve and then substitute back again, and then work. So you're getting the answer back in the negative indices. If you convert it to positive indices, for instance, here, let me show you what happens just quickly. If I were to multiply this by z cubed over z cubed, what's going to happen is that you're going to get, on top here, you're going to get z plus, if I multiply this by z cubed, we're going to get z plus 2z squared plus z 4z cubed over 1 plus 3 z minus z squared minus 3z cubed. Okay. Once you're in a situation like this, notice that it starts to get complicated now because the order of the numerator and denominator here are now the same. Before you express it in the partial fraction, now you have to divide one by the other. The transfer function has to be proper, which means that the order of the numerator has to be less than the denominator. Here it is equal, so you're going to have to divide by 1, the numerator, you have to divide it by the denominator, and then go and do the partial fractions. It starts to get a little more complex at that point. All right? So everybody following what I'm doing here? The sort of heavier explanations are given in the lecture videos that we did before, are also given in the slides. So this is just, of course, a quick review, but hopefully some of the things are ringing a bell. So any questions before we close off? We're already a little past 9, but that's something I sort of interrupted you to take calls anyway. So questions, let me hear. Any questions?
I don't have any right now, sir, but if I do have any, I'll just email it to you, right?
Not a problem. And remember, there's a discussion forum too. I think it's for this. If not, I'll set it up. But you could put questions to the class. What do you call it? That the class may be interested in, right? So sometimes if people ask me a question, or if you send me a question, yeah, I may just put it there for discussion, just to hear what the answers are. All right, because your question may be of concern to other people as well. All right.
Okay.
But absolutely,
sure.
Absolutely. If you have anything you're trying and you're not getting the answer, you're getting stuck, absolutely feel free to send me an email about it. If you have your writing or whatever it is, take a screenshot. Not 1,000,000 megapixels, but good enough for me to see and email me, and I'll write out the answer for you. Right? Or discuss the answer. We'll discuss it in class when we meet. Yeah?
Yeah, sure.
All right. So everybody else all right? We okay? Okay, so let me stop the sharing here. And I will stop it. I'm stopping the recording right now.